Most brittle materials have a different strength in tension and compression. This is the case of construction materials such as concrete, mortar, brick, and most rock-like materials. We will now see a couple of allowable stress criteria, or simply strength criteria, that were formulated in the past for brittle materials, namely the Galileo-Rankine criterion and the Moore-Coulomb criterion. There exist other criteria for brittle materials, such as the Saint-Venant-Grashof criterion, which uses the maximum and minimum normal strain at a point as critical index, or the Beltrami criterion, which uses the strain energy as critical index. But we will not discuss these criteria in this presentation, as they are not used as widely as the other ones. Historically, the first criterion that was proposed to assess the safety of brittle materials is the so-called Galileo-Rankine criterion. It is also the simplest strength criterion that can be formulated for three-dimensional stresses. Actually, Galileo proposed a criterion in terms of forces, not stresses. The concept of stress, as we know it today, was actually formulated in the 19th century, and Rankine basically restated Galileo's criterion in terms of stresses. The critical index on which this criterion is based is the normal stress acting on an infinitesimal surface passing through a point in the body. If we denote by n the unit vector normal to the surface, the normal stress sigma acting on that surface depends on n, and we will write sigma equals sigma of n. Thus, the criterion states that minus sigma c must be less than or equal to sigma of n, which must be less than or equal to sigma t, whatever the orientation of the surface is. In other words, the maximum and the minimum normal stress acting at any point of a three-dimensional body must satisfy the following inequalities. Sigma max must be less than or equal to sigma t, and sigma min must be greater than or equal to minus sigma c. But we know that one of the properties of the stress tensor is that the maximum and the minimum normal stresses at any point of the body correspond to two of the principal stresses. This is why Galileo-Rankine failure theory is also called maximum principal stress theory. We'll be using Roman numerals to denote the principal stresses, to avoid confusion with the Cartesian stresses. The principal stresses will be called sigma 1, sigma 2, and sigma 3 from now onwards. As any principal stress may correspond to sigma max or sigma min, we can rewrite Galileo-Rankine criterion in terms of principal stresses in this way. Minus sigma c must be less than or equal to sigma 1, which must be less than or equal to sigma t. Minus sigma c must be less than or equal to sigma 2, which must be less than or equal to sigma t. And the same goes for sigma 3. These three couples of inequalities define a cube in the space of the principal stresses. If the stress is plane, which means that one of the principal stresses is 0, for example, sigma 3 is 0, the criterion defines a square in the plane of the non-vanishing principal stresses sigma 1 and sigma 2. The square is not centered on the origin of the coordinate system unless the allowable stresses in tension and compression are equal. The points inside the square correspond to couples of permissible principal stresses for the material. Is this criterion acceptable for materials such as concrete? Well, the answer is only partially positive. Let us assume that the criterion has the meaning of strength criterion, which means that the points of its boundary correspond to combinations of stresses that cause failure of the material. We can compare the experimental points obtained by biaxial tests to failure on concrete specimens with the boundary of Galileo-Rankine domain. And we can see that the domain is somewhat conservative under biaxial compression. Incidentally, note that the equibiaxial compressive strength of concrete is approximately 16% higher than the uniaxial compressive strength. On the contrary, the criterion does not capture the negative interaction in terms of strength of principal stresses of opposite sign. As you can see, under combined tension and compression, this criterion overestimates the material strength.